All right, let's look at exercise 2. So this is problem 2 from chapter 11 of the course text. And so now in this problem, we're going to have a ternary system, a three-component system described using Raoult's law, which just adds an extra little wrinkle, and we'll talk about that as we work through the problem. So we have a mixture that contains N-peptane, N-hexane, and N-heptane, so C5, C6, and C7 at equal mole fractions. The temperature is 55 degrees C. Calculate the bubble and dew pressure at 55 degrees C. And then basically once we have our bubble point and dew point, in B we're asked to determine the phase. C we're going to repeat at a different pressure. And then if it's two phase, they want to know the amounts of each phase. And then D, the pressures can be adjusted so that 75% of the mixture is vapor, while the temperature remains at 55 degrees C. So basically temperature is always the same, so I'm already immediately thinking of a PXY, and at 55 degrees C we're provided with the vapor pressure of each component. Okay, so the first thing I'm going to do is this is a ternary system. All right, we haven't looked at vapor-liquid coexistence phase diagrams for ternary systems. Why? Well, because I'm not going to be able to plot them in two dimensions, right? Well, if I were to fix the composition of one of the components, then I could plot it in 2D. But I'm not going to be able to plot this in a two-dimensional graph if I have a ternary vapor-liquid coexistence, a system at ternary VLE, or ternary system at VLE. But nonetheless, okay, that's okay. So conceptually, it's still the same. So even though I have a three-component system, I'm just going to sketch a little PXY, okay, because we said it's going to be a PXY we're thinking about since their temperature is constant throughout. I'm just going to make a PXY sketch for a binary system, just so I can remind myself of what's going on. Okay, so if this were a binary system, that'd be P1 sat. Here's P2 sat, and here's my dew line. Okay, so the basic idea is we're going to know what the composition of our mixture is, right? It's equimolar of each component, right? So I'm going to know Z1. Okay, so the straight line here, that's my bubble line, right? This system, we're going to be at low pressures. We definitely have an ideal liquid, so assuming that Raoult's law is applicable seems definitely reasonable. Okay, I have a liquid up here, vapor down here below my bubble line, or my dew line. Okay, so this is my dew line, that's my bubble line. So above my bubble line I have a liquid, below my dew line I have a vapor, and in between I have two phases. Okay, and so when it comes to identifying what phase you have at given conditions, what that corresponds to is knowing your bubble point pressure, P bubs, okay, so the bubble point for that mixture, and your dew point, right, the dew point pressure for that mixture. And remember what's unique about my bubble point, okay, is that my bubble point, x1 is equal to z1. My liquid phase composition is just equal to the composition of my mixture. And at my dew P, when I do a dew P calculation, or my dew point, my vapor composition, y1 is just equal to z1. Okay? So even though we don't have a binary system, when I look at A, first calculating dew, bubble and dew pressure at 55 degrees C, what's key is it's at my bubble point, the liquid composition is just equal to the composition of my mixture. And at my dew point, the vapor composition is equal to the composition of my mixture. All right, so even though I can't draw a phase diagram for a ternary system unless I were to fix composition of one of those components, just from a binary system, all right, I can remind myself about what's special about the dew point and bubble point and how I'd go about calculating it. And then as I look at B and C, once I have my bubble point and dew point, just looking at phase diagram for a binary system, I can use that to remind myself of how I would use that to determine what phase I have. Okay, cool. Okay, and then we'll have to talk about the later part of it. Okay, so if I want to do a bubble P calculation, okay, so if I start out doing a bubble P calculation, okay, so now I have it, well, okay, and so remember, key to bubble P, let me make my note, key to a bubble P will be that Zi is equal to Xi. All right, my liquid composition is equal to the composition of my mixture. So if I have a ternary system, now we'll have 3 isofugacity equations that I can write. All right, I'll have an isofugacity equation for each component. So I will have, and again, we're assuming Raoult's law is applicable. I'll have y1p is equal to x1 p1 sat. Okay, and Raoult's law should be applicable. Okay, we should definitely be able to assume that our liquid phase is ideal. And then if I were to look at that pure component fugacity, assuming that pure component at saturation at T should definitely be an ideal gas, and Poynting correction should be negligible since we're looking at low pressures. And then likewise for the vapor phase, we should definitely be able to assume that the vapor phase is an ideal gas. Okay, so looking at my 3 isofugacity equations, okay, key with the bubble P calculation is we know x, okay, because x is just equal to z, which is 0.3333 in this case. We're given our pure component saturation pressures. What I want to solve for is P. I don't know why. Okay, so now bubble P calculation, I add my 3 equations together, and I get P is equal to x1 P1 sat plus x2 P2 sat plus x3 P3 sat. So it's still that my bubble point pressure, is just a molar average of my pure component saturation pressures, right? And again, I replace x with z. Okay, so there's my bubble P calculation. Okay, if I were to do P calculation, okay, again, what's key, right, is remembering that zi now is equal to yi. Okay, so I can write down my 3 isofugacity equations again. So I have y1p is equal to x1 p1 sat, y2p is equal to x2 p2 sat, y3p is equal to x3 p3 sat. Okay, idea being we know our pure component vapor pressures. I know y, because now it's y that's equal to the composition of my mixture. I want to solve for p, right? This could be p do, since y is equal to z. What I don't know is x. I don't know x and I don't know p. I don't care about x at this point. I only care about p. And so the trick is we're going to divide through by p1 sat, p2 sat, and p3 sat so that we can add our equations together and kill x in the same way by taking advantage of the fact that our mole fraction compositions have to sum to 1. So I'll rewrite this as p times y1 over p1 sat is equal to x1, p times y2 over p2 sat is equal to x2, and p times y3 over p3 sat is equal to x3. Okay. Sum the equations together. I'm going to write a big bar so I get more space. Okay. Liquid phase mole fraction sum to 1. Okay. Factor now p, I just get p times y1 over p1 sat plus y2 over p2 sat plus y3 over p3 sat is equal to 1. Okay. So finally, okay, if I were calculating p do would just be the inverse of this, y1 over p1 sat plus y2 over p2 sat plus y3 over p3 sat inverse. All right, so I can solve for p. Oh, and again, you know, y1 is equal to y2 is equal to y3 is just equal to 1/3, right, in this case, since it's equal molar. Okay, so basically then, now I know p bubs and I know p do. Okay, so then the first thing when I'm looking at B and C is it wants to know what phase we have. So so if we have a pressure of 1.7 bars, okay, and temperature is the same, if my pressure is greater than P bubs, then I have a liquid. If my pressure is less than P do, I have a vapor. And if I'm in between, I have two-phase. Okay, so it's just seeing where my pressure lies in relation to P bubs and P do. Okay, cool. And then the second part of that is, say we had a two-phase system. So it says if a two-phase system, calculate the amount and composition of each phase. Okay, so So where things get a little more difficult, okay, so let me write down our isophycacity equations on another sheet, okay. So what I'm going to do is I'm just going to write down my isophycacity equations and talk about the little subtlety that we need to worry about for systems with more than two components, okay. So my isophycacity equations take the form of y1p is equal to x1 p1 sat, y2p is equal to x2 times p2 sat, y3p, and actually let me just look at the binary system just so I can draw the analogy. Okay, so the difference is going to be when I have a binary system, okay, so if I look up here, right, let's look at the problem. So basically we're given a temperature and pressure and asked what our phase is. Well, so if we're given the temperature and pressure, so if we're given T and P, okay, and if we're given a T, if that pressure puts us in the two-phase region, basically we want to solve for Y and X. What's the composition of the two phases? Okay, so if I just think of a binary system, if I know T, it means I know P1 sat and P2 sat, okay? And so I'm going to say binary, and I'm going to say given T comma P, right? Solve for Y1 and X1. Okay, so basically if we're given T and P, T means we know P1 sat and P2 sat, I know P here. Okay, so now to be rigorously correct, okay, right now I have two equations with four unknowns. My unknowns are going to be Y1, Y2, X1, and X2. Right, I have two equations with four unknowns. I can't solve them as is. Okay, what we've kind of been skipping, so far, or kind of doing on the fly, is, well, this is solvable because I know that I have constraint equations that y1 plus y2 is equal to 1 and x1 plus x2 is equal to 1. All right, I have constraints, and then I know my mole fractions have to sum to 1. Okay, so when I write down my two constraint equations that my mole fractions have to sum to 1, okay, now I have four equations with four unknowns. Okay, so I have four equations with four unknowns. Okay, but now let's think about the same thing for a ternary system. Okay, so we're going to have a ternary, okay, a three-component system, and given T and P, all right, again, we want to solve for, I'm going to say yi and xi, the vapor phase composition and liquid phase composition of our phases. Okay, so where things get more complicated now is, okay, I'll write down my isophycacity equations. Y1p is equal to x1 p1 sat. Y2p is equal to x2 p2 sat. Y3p is equal to x3 p3 sat. Okay, so if I just look at this as is, okay, so if I know temperature, then that means P1 sat, P2 sat, and P3 sat are known. Right? I calculate those, say, via an Antoine equation. Okay, P's known. Okay, so right now I have three equations with six unknowns. Right, y1, y2, y3, x1, x2, x3. So I have three equations with six unknowns. Okay, if I look back to what we had for binary systems, I have two constraint equations. Okay, my two constraint equations are that my mole fractions have to sum to 1. So here that'd be y1 plus y2 plus y3 is equal to 1. x1 plus x2 plus x3 is equal to 1. Okay, but still, all right, that only gives me 5 equations. So I have 6 unknowns and 5 equations, so it's not solvable. I can't solve it to find a unique set of compositions. All right, I have 6 equations with, or 5 equations with 6 unknowns. Okay, so I have more unknowns than equations. So what am I going to do? Well, what we haven't taken advantage of yet, okay, is we can add to this our mole balances. Okay, and if I picture a flash drum, okay, and so what's going to happen is we have more than 2 systems. We can't solve our isophycacity expression independent from our mole balances. So if I have a flash drum, okay, And so the flash drum operating at a given temperature and pressure so that I have a vapor and liquid stream leaving at saturation. So in would go some feed of composition Zi. Okay, well, let's write Z1, Z2, Z3. Okay, so I should also say in both of these problems we were given the composition of our mixture. Then out I'd have a vapor, composition Y1, Y2, and Y3, and a liquid of composition X1, X2, and X3. Okay, so what I need to do is looking at this, setup. Okay, I don't know the amount coming out vapor or liquid or the compositions of each. Okay, I know the composition of my mixture. It's just 1/3, 1/3, 1/3, and 1/3. Okay, and then basically we don't know F. Okay, but what we typically do is we just assume that we assume a basis of F is 1. Okay, so we assume a basis of F of 1, right? So when we solve for V and L, it'll really be whatever we calculate for V will be relative to an F of 1, right? So it's really not V an amount vapor. It's really a fraction vaporized, the amount of that initial mixture that's vapor. Okay, so we know our Z's, and then since we're not given an F, we assume a basis of F of 1. So we calculate V and L relative to an F of 1. Okay, so all right, now that we drew the schematic, if I have a ternary system, how many independent mole balances can I write? 3. All right, and so you can write any 3 you want. Let's just write Z1F is equal to Y1V plus X1L. Z2F is equal to Y2V plus X2L. And then it could be, F is equal to V plus L, or we'll just write the same thing here. Z3F is equal to Y3V plus X3L. Okay, and so now if I count up equations and unknowns, right, now I have 1, 2, 3, 4, 5, 6, 7, 8 equations. All right, so I'm going to have 8 equations. Okay, then in terms of number of knowns, then I'll have, if I look back at our original system, so originally, where did my pen go? I had 1, 2, 3, 4, 5 equations, and how many unknowns did we have there? We had 6, right? Y1, Y2, Y3, X1, X2, and X3. Okay, so I had 6 unknowns. How many unknowns did I introduce in my mole balances? Well, I know all my Z's, okay, so those aren't unknown. F, remember we took a basis of F of 1, so that's not unknown. If I look at this right-hand side, we've already accounted for not knowing X1, X2, X3, Y1, Y2, and Y3, so those have already been accounted for in our list of unknowns. But basically we just added 2, L and V. Okay, so we added L and V to the mix, so that's going to give us a system of 8 equations with 8 unknowns. All right, so if you compare your pressure to your bubble point and dew point pressure, and you find that you're in the two-phase region, then what you need to do is simultaneously solve these 8 equations with 8 unknowns. Okay, so in addition to getting all your Y's and X's, you're also going to get V. Okay, and remember by V, it's really V over F, right? The fraction coming out vapor, or the fraction vaporized. And then you're going to get L over F, right? Because this could be relative to value of 1. So when you come up here then, and it wants you to know the amounts, if it's two-phase, again, it's just you have to simultaneously solve those 8 equations with 8 unknowns, right? And I'll leave it up to you how you want to solve it. If it were MATLAB, yeah, you could just throw it in FSolve if you wanted to. But you could solve that sequentially, I'm sure, if you wanted to give it a try. So that's B and C. If you find yourself you're in two-phase, you need to solve those 8 equations with 8 unknowns. And so what's different compared to binary systems is now you need to simultaneously solve your mass balances along with your equilibrium expressions, and that's where you get the amount that's liquid and vapor. And then D, So now you're told the pressure is adjusted. So now, so you're going to change the pressure so that 75% of the mixture is vapor. Okay, well, the temperature remains 55 degrees C. And so basically, it's going to come back to solving the same system of 8 equations. But now what's going to happen is you don't know P, but when you hold 75% vapor, 75% of the vapor, right? So what's going to change is now you don't know P, okay, but you know that V is equal to 0.75. Okay, so you know V now is 0.75, and you don't know P, so you're going to solve for P along with L, which is 0.25, and your compositions of each phase, right? And yeah, if you wanted to, then that one becomes easier if you want to solve it by hand, because if V is 0.25 and L is, if V's 0.75, L's 0.25, so essentially you've just applied, your total mass balance, as if instead of this, I'd use a total mass balance equation, F is equal to V plus L. I eliminated an equation that I would need to solve, okay? But yeah, there's no other way around it. Then you end up with 8 equations, 8 unknowns. For when I have more than 2 components, and I'm in two-phase coexistence, I'm forced with solving my mass balance simultaneously with my isophycacity equations, where you assume a basis of F is 1, and you solve for the amounts of your liquid and vapor phase, right? And so that's when you have more than 2 components. Again, there's no real equations to memorize. It's just we realized we were stuck, and so I just drew a simple flash drum, right? Because when I think about a TXY or PXY, and you're trying to figure out what happens at the isotherm or isobar, I just picture a flash drum, right? And that's how I was able to walk through what are the relevant mole balances that I can write, okay? But that's it, right? It's just a little more involved when we have more than 2 components.